And now we come to our next speaker, and it's my pleasure to introduce you all to Michael Bonner from St. Clair Systems, where he is the Vice President of Engineering and Technology. He started his professional career with a degree in electrical engineering, and over the years has spent time in a wide variety of industries, including audio systems, medical equipment, and metal stamping, to name just a few. The list is longer. Today, however, he is here to ask you all a simple question. Is UVEB the answer to the EV question? And I suppose you also have an answer for us there.
I'm going to try.
All right, we'll see. The floor is yours.
Thank you. We're excited to be here. I was one of the ones that voted that way right at the beginning. Because the changing electric vehicle landscape faces considerable challenges. And there's energy density, there's charge time, range anxiety, right down to the source of energy in the first place. So all of these things are related to energy, thus the title. We're going to look at UVEB technology as a method of providing greater durability, thinner films. This means lower weight. That means longer range. And it gives you reduced waste and increased throughput. This reduces costs, and you can actually reduce as much as 95% over conventional coating technology. So it's going to be interesting to look at how that affects the cost of the end product, which of course determines its market penetration in the first place. So at the end, we're going to do a quick example of how this coating is applied in the, how this coating technology is applied in cathode-anode performance and how it affects the overall battery process. So let's get started. Why is energy an issue? The world's thirst for energy is well documented, and as you can see here, despite conservation efforts, annual global demand has increased more than 67% over the last 3 decades. Now, this graph goes through 2021, and obviously 2020 would be my 3-decade point, but we wanted the 2021 point in there to demonstrate that this trend continues. We had an anomaly in 2020 due to the pandemic shutdowns, 4.5% reduction in energy demand. That completely eclipses the 1% reduction that we saw in 2009 after the Great Recession. So it's also apparent from this graph that the greatest growth came in Asia. Now, we can see that China, India, South Korea, Iran, Indonesia, they all experienced triple-digit growth over these 3 decades. This is the result of increased industrialization in those areas. Germany, Japan, Russia, all decreased their energy consumption. And this is a result of some outsourcing and some conservation efforts. So there's a combination there. And then South Korea, Iran, and Indonesia, they weren't even in the top 12 in 1990. And Italy, Ukraine, and the UK are no longer in the top 12. And again, this is a combination of moving processes to Asia and also through conservation efforts. Now, I don't want to bring back any bad memories, but we just went through another energy crisis. And despite concerted efforts to move to clean energy sources to reduce the impact of energy on our global environment, the demand has simply grown too fast. It's outpaced our ability to create a clean energy supply. The result is that energy supply is just as susceptible to geopolitical issues today as it was in the 70s. In November of 22, the Adhesive and Sealant Council noted that global energy markets are in an upheaval, led by geopolitical conflicts, macroeconomic issues such as high inflation rates and supply disruptions. Nowhere is that more apparent than here in Europe, where the cost of energy skyrocketed due to the war in Ukraine and the resulting sanctions against Russia. In October of 22, Gary Vasilash of Gardner Business Media's On Automotive wrote, since Q1 of 2020, Natural gas prices in Italy, Germany, France, and the UK have increased an average of 2,183%, with wholesale electricity prices up 1,230%. I probably don't have to tell you that. But the result is that the cost of energy to produce an automobile increased by about 1,700%. It's a huge deal. But this isn't limited to just Europe. The NERC, also in November of 22, talking about the US, said that power shortfalls could be rife over the next 3 months across a large portion of the North American bulk power system, particularly during extreme and prolonged cold conditions. Now, we dodged a bullet. We had a fairly mild winter across Europe and North America last winter. But we can't rest on that. We need to view that as a shot across the bow. And we clearly need to continue to migrate to solutions that are more energy efficient and support clean energy. Energy-curable technologies do that. They offer an attractive solution for a host of reasons we're going to talk about now, and amongst those is increased energy efficiency compared to conventional coating processes. So that's a pretty good overview of why energy is important. So by now you're probably going, okay, so who is St. Clair Systems and what have they got to do with all of this? We design and manufacture advanced temperature and viscosity control systems for industrial fluid dispensing processes. That's a mouthful. We've been doing it since 1990, so over the entire horizon of this analysis. We specialize in all different types of systems, recirculating, dead end, and we work with everything from solvents and water down around 1 centipoise, all the way up to high viscosity adhesives in excess of 1 million centipoise. So we do paints, sealers, adhesives, and pottings, encapsulants, foam, you name it. So who cares? And the answer is lots of folks across myriad industries, as you can see here. We've got automotive, we've got aerospace, we've got food packaging, we've got nanomaterials, we've got cabinetry, pharmaceuticals, you name it. These are demanding customers with really difficult processes. And what we've learned is that there are ramifications to not controlling temperature and viscosity in virtually every fluid dispensing application out there. So that's our stake in this game. We're all about fluids. So if we look at the modern automobile, where are fluids used? And this is a nice slide from our friends at PPG, and it shows a pretty good list of where fluids are used. And I think it's easy to say they're used just about everywhere. But this graphic really puts it into perspective. While it's focused on greenhouse gas emissions, remember that these are all the result of energy consumption. And this shows what everybody in here already knows. The paint shop is the largest consumer of energy in the assembly process. And it accounts for about 50 to 90% of the energy used in an assembly plant. Now, this also shows that the majority of greenhouse gas generation takes place as a function of fuel production and consumption over the life of the vehicle. And as is noted here, that's the reason for electrification in the first place. But what isn't noted is that this electrification process moves some of this part of the greenhouse gas emissions back into the material selections at the beginning of the process. So it moves it upstream, primarily because of the battery manufacturing process. So while we know this is important, the paint shop, and there's a lot of work being done right now on working on the paint shop, but today we're here to talk about batteries. So we're going to focus our attention mostly in this area here. And this is a pretty nice list of the fluid consumption in a battery pack manufacturing process. So when you're constructing them, these are the fluids that you're going to see. And as we're talking about the evolution of battery packs, we're going from separate packs, separate modules, through cell to pack, and into, and we'll see more of this as we go through the next 2 days, to battery packs directly in the chassis. Now, this is great. It reduces weight, that extends range. We already talked a little bit about that. And it reduces cost, which extends market viability. We talked a little about that. But it also comes with some serviceability and recyclability issues. And you have to be sure that you get everything right up front because they become very difficult to go back and service. So now let's take a look at how UVEB technologies impact these objectives. We have to start by comparing thermal and energy cure technologies. Now, conventional coating technologies are thermal cure. We're talking about materials like solvent-borne, waterborne, powder coat, and they're all cured by baking. Elevate the temperature, drive off the solvents or melt the powder, and then start the cross-linking process. Now, the problem is that this requires a lot of energy. You've got to heat the air in the oven, you've got to heat the parts, you've got to heat the coating. And so this requires a lot of energy. Specifically, when you're talking about solvent-borne organic materials, you're talking about the emission of VOCs into the air in the oven. And that brings up a couple of issues because VOCs, by their very nature, are flammable. That's that volatile part. And so we can't just let it build up or we have an explosion hazard. But the other problem with VOCs is that they are hazardous to the planet and to the life on it, which we kind of appreciate the life on the planet, so we don't want to release these directly into the atmosphere. This means that they have to be remediated, usually through incineration, through a regenerative or recuperative thermal oxidizer, or an RTO. So we have to burn them off. And we utilize the fuel potential of the solvents in the airstream, but that usually has to be supplemented by natural gas, which increases the usage for conventional technologies. Looking at energy cure, on the other hand, we're talking about materials that are usually named UV, UV LED, electron beam, and these are cured differently. The cross-linking process is initiated by exposure either to high-intensity light, usually in the UV band, or to a stream of high-energy electrons. And this is directed at the coating, not at the substrate. So it is far more efficient, and so it reduces energy consumption, in many cases by as much as 95%. So we're talking a huge change. And because these are 100% solids, there are no VOCs. This means we don't need to remediate, and this means that we don't have to spend the energy to remediate. We don't have to spend the capital to remediate. So where did this technology come from? Often, this is thought of as something new. And in reality, it all started with electron beam technology. This was developed by Edwin Newton, of the B.F. Goodrich Company, back in the 20s. And he developed a method of using high-energy electrons to vulcanize natural rubber. And he filed for a patent in 1929, almost 100 years ago. This process is still in use today in the tire industry. And so this technology was born of the automotive industry and is still in use here today. Now, UV as a curing medium became prevalent in the back in the 60s, and it actually underwent commercialization in the 1970s, driven primarily by the oil embargo by OPEC in 1973. HG Experts put out an article that was an introduction to UV and EB technology, and in that report they stated The commercialization of UV curable inks in the 1970s enabled beverage companies to accommodate a reduced availability of natural gas with a technology that depended solely on readily available electric energy. And at that time, a lot of that electricity was coming from nuclear. And you've still got some of that over here. We have very little in the US. This represented the first direct-to-metal applications. It was just in a simple beverage can, but it demonstrated the capability of the technology. And since that time, countless other industries, including automotive, aerospace, and many others, have recognized and exploited the advantages of energy cure technologies in their process. So, what are those benefits? Well, advancements in chemistry over the last 50 years has made an extensive number of options available to formulate coatings with a wide variety of cured film properties. And this makes energy curable technology available for virtually any application. Now, in addition to the lower energy usage and the natural sustainability because of the lack of VOCs, this technology also offers increased durability with thinner films than you get with a conventional technology. So you get superior protection out of this technology. Speed. The cure is instantaneous, and I'm talking seconds rather than minutes, hours, and days as you have with conventional technology. And that means you can move to the next steps in the process more rapidly, and this increases your throughput. Increase first pass yield. Because you have fewer handling issues. You're completely cured, so you don't have scratches, you don't run into problems with blocking, and other things that happen that create rework and scrap in the process. So that's extremely important. Footprint. These systems are significantly smaller, and we'll look in more detail here in a minute, because they don't need all of the large RTOs, ovens, etc. Less waste. And this is an interesting one. Everybody thinks of powder coating and the ability to reclaim it and reuse it. What they don't realize is that being 100% solids, UV and EB type materials can also be reclaimed and reused. So you have less waste from the process. And then, of course, my topic for the day, clean energy support. Reduced demand on the grid just because you don't need as much energy. You're actually addressing it at the very fundamental demand level, which is really important. So I promised an example of how this all comes together, and so let's take a look at that right now. And it's in the battery manufacturing process. We call it the Miltech electrode example, and Miltech UV did this work in conjunction with the Argonne National Laboratory and the Oak Ridge National Laboratory in the US. We're going to drill all the way down to the cell level, and you already saw some of this information in the first presentation, but we're going to drive down to the cell level and take a look at the three different types here that make up the typical battery pack. They're all similar in their construction, but we're going to focus on the standard cylindrical cell, and we're going to do that for a couple of reasons. One, it's the one we're all familiar with. We've been playing with them since we were kids, getting electric toys for Christmas, and it's becoming rapidly the fundamental unit from which battery packs for EV are constructed. So when we look at the electrode structure, we can see that we have an aluminum layer, and it's bonded to our cathode material. And this is separated by a separator from the anode material, which is bonded to a copper film. And then this is, and I'll use the term filled, with an electrolyte, which promotes the movement of electrons. The coating on each electrode pair determines the performance in application. And so it's extremely important at the cell level because it gets multiplied thousands of times in the conventional battery pack. Now, traditionally, electrode coatings are solvent-borne PVDFs, and they do a good job, but they come with baggage. They're thermally cured, and that means that you've got to, again, have large ovens to bake them, so they're slow to process, and they require a lot of energy. And because they're solvent-borne, they emit VOCs, and we have to remediate those and deal with them. Because of that, we have a high capital cost, and because we're pumping a lot of energy in, we have a high operating cost. Now, when we compare the footprints between conventional and UV processes, we can see the ovens, and these will be tens of meters long. And we don't even show the RTO here, which is usually located outside the building, but also takes up a lot of space and a lot of capital. The UV process, on the other hand, is significantly smaller, an order of magnitude often. So you've got reduced space. The equipment is smaller, it's less expensive. It requires less energy, so it's more efficient to operate. And one of the important things here when you look at it, because both sides of the electrode can be coated simultaneously and cured at higher speeds, your throughput from this smaller footprint is about 4 times what you get out of the conventional process, which is why you see 4 ovens up above. Duke Ellington said, "Don't mean a thing if it ain't got that swing." What he meant was it's all about the performance. And so it doesn't do you any good if you can't get similar performance out of these coating technologies. Here we can see that the UV-EB coatings that were developed for this application perform as well or better than the commonly used PVDFs. It also doesn't help you if you can't do all of the components. Because if you can't do everything in the stack, then you have to have the ovens and RTOs for some and not for others. So looking at that, they were able to develop UV applications for all components in the stack, the separators, the anodes, the cathodes, etc. But here's the money slide, okay? Converting from standard thermal cure PVDF to UV resulted in no loss of performance, 4 times increase in throughput, over 80% reduction in energy cost, over 80% reduction in manufacturing cost. And when you combine that manufacturing cost with the materials involved, it reduced the cell cost by nearly 25%. So that's significant. Complete elimination of VOCs in the process, over 60% reduction in capital cost, and over 70% reduction in footprint. So we've shown that there's a lot of opportunities to utilize this type of technology in EV manufacturing. And it all starts with the cells that are the base of the technology. And that represents a significant portion of the cost. And with that, I want to thank you for your attention and open the floor for questions. Thank you.
Thanks very much. And let's see if there are any questions in the room. There's a first one.
Yes, good morning. I'm Daniel Neuse from FFT Production Systems. We are a line builder for module, pack, and housing lines. And I understood that the UV lamps will be a big thing in regards to the drying and those kind of processes. But what about the activation process of materials? Do you think this will be a big thing as well?
The performance was comparable, and I'm not a chemist, and I don't know exactly how all that works in the process, but can certainly put you in touch with the people who have done the work and can answer those questions for you. Okay?
Thank you. Are there more questions in the room? Yes, please.
So my name is Holger Fricke from Fraunhofer IFAM. Thank you, Michael, for the very interesting talk. You stressed on your last slide the costs, energy savement, and so on. What is about the material costs that you have? You need an accredited chemistry normally for UV curing, so the prices are higher. And did you calculate this also?
That's absolutely correct. And people get hung up on the cost per gallon. for instance, or cost per liter, since I'm over here. The cost per liter of 100% solids materials is higher. But if you're running a 50 to 55% solvent load in your conventional coatings, you're using twice as much. And you have to deal with all those other materials. You got to deal with the solvents when they come out. So it ends up being significantly cheaper in the final application, even though you pay more for the fluid up front. You're using all of it, and you're not losing it to overspray, losing it to other application losses. So it's a great question, though.
Thank you. Hang on a second. I'll get to you next. Before that, Dirk, do we have any questions from the remote audience? Not at this point. Okay.
Hello, it's Shanta Desai from representing Nissan. In the beginning, you said that the car production energy is increased by 1,700%. Is that right? And then in your results, you claim that 80% reduction in energy cost. Are we talking about 80% reduction in cost based on the 1,700% increase? Have I missed something?
No, they're completely separate. What we're really talking about is consumption. And that's kind of cost independent. So if you're reducing your consumption by 80 to 95%, then you're reducing your costs accordingly. As cost goes up, then that represents a larger chunk of dollars. But we're basing that all on the volume of usage, not on the cost itself. Probably wasn't clear in my slide, sorry.
Yeah, okay. There was a bit of confusion there. Thank you.
Thank you. And we have time for one more question, in case that's of interest. Okay, nothing from the remote participants either. In that case, thank you very much. One last applause for our speaker, please.